So far, we looked at the differences between narrative reviews, systematic reviews, and meta-analyses, interpreted the results of a meta-analysis in a forest plot, visually assessed the variability of body of studies in a meta-analysis, and interpreted the statistical tests of heterogeneity. Now, let's assess the risk of bias in the body of evidence provided in a review, which is course learning outcome number 5 on the course syllabus.
So there are different types of biases. So there's measurement bias, there's selection bias. Two that are really important when you look at systematic reviews and meta-analysis is the reporting bias and publication bias. So reporting bias is a skew in the availability of data such that observations of a certain kind are more likely to be reported. And publication bias is the tendency for published studies to be systematically different from all completed studies of a question. Published studies are more likely to be positive. I know this is usually because one thing is the editors of journals find positive studies to be more interesting. So for example, positive we mean if the study actually found a difference. So if a study didn't find a difference, usually it's not it's not exciting news. So typically editors may not choose those studies to be published. That's not always the case, but we're saying typically. The other thing is, the people who actually doing the study, if they didn't find what they were looking for, it's likely that they're not actually going to submit it for publication. Whereas if researchers actually found what they were looking for, then they're excited about it, so they will actually submit it for publication. Now here are the more information about reporting bias and publication bias. I let you read those. The consequences of publication and reporting bias can corrupt the body of evidence, usually exaggerating estimates of magnitude of treatment effect. Meta-analyses that fail to identify and include unpublished studies face a risk of presenting overly confident estimates of treatment effectiveness. The risk of publication bias is probably higher for systematic reviews and meta-analyses that are based on small studies. Small studies are more likely to produce non-significant results due to lack of statistical power and are easier to hide. Now, larger studies are not immune either. So sponsors and authors who are not pleased with the results of a study may delay publication or choose to publish their study in a journal with a limited readership or a lower impact factor. Now, in general, there are 4 strategies to address reporting bias. You can either examine whether the smaller studies show bigger effects, for example, use a funnel plot, and I will talk about funnel plots in a little bit. Can reconstruct evidence by restoring the picture after accounting for postulated publication bias, estimate the chances of publication according to the statistical significance level, or examine the evolution of effect size over time as more data appears. Now, funnel plots are basically in a figure that relates the precision of studies included in a meta-analysis to the magnitude of treatment effect. The resulting display should resemble an inverted funnel, and I will show you a picture in a little bit. Such funnel plots should be symmetric. So it's important to think of it as symmetric. Around the point estimate, dominated by the larger trials or the results of the largest trials themselves. Now, a gap or empty area in the funnel suggests that studies have been conducted and not published. Because visual determination of symmetry can be subjective, meta-analysts sometimes apply statistical tests for the symmetry of the funnel. And that statistic test that they use is called the Eggers test. So with the Eggers test is usually it's used to statistically examine the funnel plot for asymmetry. So again, it's always makes it easier if you think of the null hypothesis. So always the null hypothesis means there is no difference, right? So in the Eggers test, we're looking for the symmetry in the funnel plot. So if there's no difference, that means the plot will look symmetric. So the null hypothesis would be that symmetry exists in the funnel plot, with the alternative indicating that asymmetry is present. So in this case, we also do not want to reject the null hypothesis, because we want this to be symmetric. We want them to be the same. So because of that, we also are looking for a p-value of greater than 5%. So just like when we looked at the test for heterogeneity, when we wanted the studies to be similar, so we looked for a p-value of greater than 5 or 10%. The same is true in the Eggers test. We want symmetry, because asymmetry means there is publication bias. So that's why a p-value greater than 5% is ideal. And here's what the plot looks like. So here's the magnitude of the effect. So let's say this is the line of no difference, and then different studies can find different outcomes, right? So either in favor of one group or the other group, and then overall we want this to look like symmetric. So as you can see, this kind of look, if you draw a line here, so you can draw a line, and this would be, roughly speaking, this is kind of symmetric. So it kind of looks like an inverted funnel. Now this one, on the other hand, there's no symmetry here. So there's no, if I draw a line here, it goes through, or it's hard to draw a line, right? Because if you draw a line, I'm not sure how to draw the line here to make, so there's no way to construct uh, a funnel here. So because this is not symmetric, if you just look at it visually, you can say that there's publication bias. So the previous one, it's more symmetric. So there is no publication bias if you look at this funnel plot. And this one, it's hard to make it symmetric, so there is publication bias.